Sequential logic is digital logic that has memory in it. So so you've got combinational logic where the outputs are a function of only the inputs, and sequential logic where the outputs are a function of both the inputs and the input history. So in sequential logic, you have some kind of memory in the circuit. Now there's a couple of weird terms that can be confusing. So technically, as I mentioned, sequential logic is where the output depends on the present value of the inputs in the sequence of past inputs. It implies that there's memory. Synchronous sequential logic is when, specifically, where you have sequential logic that uses a clock. So you could technically have sequential logic without a clock, asynchronous sequential logic, but no one's ever really gotten that to work, unfortunately. It would be great if it worked because the clock consumes a lot of power in chips because the clock is distributed all over the chip. So if you could come up with a practical way to build sequential logic without a clock, that would be a $1 billion idea because that would make chips consume much less power. But the much easier way to do it is with a clock. So basically, you've got a clock that's synchronizing all the sequential logic. And then you've got this term state that I'll use a lot, which is all of the information in the circuit that's necessary to explain future behavior. It's basically the contents of the memory that have to be registered inside the circuit. And the memory itself is built with either latches or flip-flops. Did you guys talk about latches and flip-flops in 211? Mm-hmm. Oh, you did cover that? Okay, good. Okay, so before I talk about that, in Verilog, there's two ways that I know of to create a memory in Verilog. The first way is to have an always, or actually what I should say is there's two ways to describe a logic circuit that has memory. Both ways use the always statement. So in the first case, I have an always, and it says always at pos edge clock, A gets B. Why does that have memory? It's because B is an input in that always, but it's not part of the sensitivity list. So if B changes without the clock, positive edge of the clock, then that circuit has to remember the old value of B from when you got the clock edge. Does that make sense? The other way is if you have an always at star, so this looks like a combinational logic always. So always at star, star means that anything that's treated as an input in the always, the circuit will be sensitive to. Right? So that should be combinational logic. However, problem is if you have an if statement in there that forgets, that causes the always to trigger, but not assign one of the outputs. So in this case, C is an input, B is an output, A is an input, right? So A is an input because it's part of a condition. C is an input because it's on the right-hand side of an assignment, and B is an output, right? The problem is that if any of those, if A or C changes, it'll activate the always. But when it's activated, if this if statement is evaluated false, if this if condition is evaluated to be false, then I don't assign the output, right? You guys see that? So the always may run without ever assigning its output, B. So that has to create memory because that means that B has to hold on to its old value, whatever it was last assigned to. So even though it activates on all the inputs, it doesn't necessarily assign, it doesn't assign all the outputs whenever it's activated. So to summarize that, you can either have a sensitivity list that doesn't include the inputs, or you can have a control flow inside the always that doesn't always assign every possible output every time the assign is activated. So in this case, this is going to create, that first option is going to create that ends up creating a flip-flop because it activates on the edge of the clock and it synchronizes the clock. The bottom one creates a latch because it's using A to control whether or not the output gets assigned. So A is kind of like the clock in the second example. I don't call it clock, I call it A, but it's effectively a clock for a latch. Okay, so I've got, on this timing diagram, I've got clock and D. D is the input, and Q is the output. And I've got two always statements, which are the same two I showed you before. I changed the names of the signals here. So in the case of a latch, I say always at star, if clock equals 1, then Q gets D. And in the second one, I said always at pos edge clock, if clock equals 1, then Q gets D. Make sense? So how do these work? Well, in the latch case, anytime the clock is high, the D input will move straight out into the Q output, right? So in other words, in the latch case, the Q is doing whatever D is doing, essentially, right? Q is always D, right? When the clock is high. But then when the clock is low, like it is here, clock is low, D changes, Q doesn't. You see that? So the clock, when the clock is high, D propagates straight out to Q. When it's low, it doesn't. Of course, in this case, there's no change. At this point, there's nothing interesting going on here, right? When the clock is low there, because D doesn't change. But when the clock is low over here, D does change, but Q doesn't correspondingly change, right? Now, in the case of a flip-flop, whenever you have the rising edge of the clock, it's like taking a snapshot of D. So rising edge of the clock will sample whatever's on D. So in this case, rising edge of the clock, D is low, and the output is going to go low, right, in response to that. Any other time that D can change, and that won't change Q. The only time that Q will change is on the rising edge of the clock. In this case, Q, you have rising edge of the clock here. D is high. Q was low and transitions to high in response to that. You guys see that? So in the case of the latch value, now at the beginning here, both of these are don't knows. Notice that there's a line on the top and the bottom because I don't know what Q is at the beginning. I don't know what the initial condition here of Q is. But the first time Q changes the first time I know what Q is when we have D, actually right here, D, when clock goes high initially, D is low. That will ensure that Q goes low. D changes while the clock is still high, and that will cause Q to go high, right? And then in the flip-flop, you just have to look at the rising edges of the clock to see where the corresponding changes in Q are. Does that make sense? Okay, so the problem is that you don't want to ever use latches because latches complicate timing. FPGAs can support latch behavior, but if you want to maximize your clock rate, you want to use flip-flops. Make sense? So you should avoid latch behavior in your code unless you really want it. But in this class, you should avoid it, right? Which means that if you use always underscore com, that's good because then the compiler will give you an error if you have a latch in there. If you use always at star and you have a latch accidentally, you won't get an error message. I think it does generate a warning though in model sim because latches are generally, not something you should use in general. Okay. If I have code like this and I want to avoid that latch, all I have to do is put an else here, right? And problem solved, right? If I put an else on this if statement, I don't have a latch anymore. You just have to ensure that all the outputs get assigned no matter what control path is taken through the always block. You guys with me? Or you could put a default, you could assign Q before this if statement to some default value and then have it redefined in the if statement if needed. Okay? Okay. Now, if you have multiple flip-flops in parallel that effectively create a multi-bit flip-flop, that's usually just referred to as a register. But it's confusing because we also have registers in the register file. So there's two types of registers. There's a register that you have in your circuit, which is a multi-bit flip-flop, multiple bits in and out, and, you know, D and Q having multiple bits. And then you have registers that are in like your assembly language in your a register file, right? So those aren't the same kind of register. The register in your register file is actually a RAM, but they're still called registers. So when you're in microarchitecture, like designing a circuit and you have a register, it's just basically a flip-flop. But if you have a register in your software, then you're referring to a location in the register file RAM. Okay, so we talked about, I showed you examples like this before where you could create a flip-flop really easily in Verilog. You just say always at FF. And again, the underscore FF is just, it's optional. It's just there for you to be able to give the compiler a hint or the synthesizer a hint on what you're intending to do. But always underscore FF or just always at pos edge clock. Q gets D, that creates a register. You can put that in its own module like it's shown here, or you can just inline it inside your another module, which hopefully you guys are already doing for lab 3. You can also have enabled flip-flops that have an additional feature where you have this enable input that if the enable is low, then it will ignore the clock. And if the enable is high, it'll just act like a regular register. You guys with me? So do we need to use this in lab 3? Yes, this is for your IO2 out. IO2 out. So you have one register in there, at least one register. Is there another one? I think there's just one. So there's a register that drives the hex displays. The only time that register should be enabled is when the CSRRW instruction is in the execute stage and the immediate field is 2. That's the only time that register should be enabled. Because otherwise, the hex displays would be changing every cycle, and they would be changing to, I think, the contents of the RS register. So if you always enable the IO2 out, if you have it always enabled, then whatever your register file happens to be spitting out on the first read port is going to be shown on the hex displays, which means it's going to be changing at up to 50 million times per second. So, you know, it's going to be changing so fast, I think it'll probably just look like 8s or something like on the hex displays. So you want to make sure that you only update the hexes during those points in time when you want to update it, which is when you actually execute that instruction to update them. Otherwise, you want to lock that value in and hold the value of the hexes while other instructions are being executed. And then there's also a feature for resetting. You can have a reset input where it'll reset the register to 0. You want to have that for your program counter. So when you reset your machine, your CPU, it should reset the program counter to 0 and start executing instructions at address 0, right? If you don't do that, you probably won't notice, because if the program counter is not resettable, it'll just keep counting and eventually get to 0 anyway, right? So you probably wouldn't even notice if you didn't have a reset on there, but when you get your branch and jump instructions, it's important to have it, because if the program counter comes up in a random value, you might end up in a part of your program where you're kind of in an infinite loop and you never do roll back to 0, right? But right now, when you don't have branch and jump instructions, then you're guaranteed to eventually get back to 0, right? Because it's just counting up by 1. You guys with me? Okay. And the reset can be synchronous or asynchronous. So if you put the reset in the sensitivity list, that allows you to reset it independent of the clock. Do we care about that? I haven't seen a case where that matters in this lab, in this class. I don't think it matters whether your program counter has a synchronous or asynchronous reset. I don't believe so. I usually just make it asynchronous, just that way it resets immediately when you hit the reset button. But I don't think I don't know if it'll make any difference if you make it synchronous. I don't think so. So basically, just to explain, if you have a if reset inside your always, you can say if reset is asserted, then set Q to 0. Otherwise, set Q to BD. And then the sensitivity list can either have just the pause edge clock or the pause edge clock and pause edge reset. Make sense? And I don't even know if you need pause edge reset. Could just put reset here, right? I mean, if you execute the always when reset goes from like high to low. Oh no, you don't want that, because if you did that, then it'll change Q actually, right? So you do want pause. Sorry, you do want pause edge reset, because you don't want it inadvertently have the falling edge of reset update Q. Make sense? You guys with me on that? Okay. Okay, that's just a D flip-flop with reset and enable. And then you could do other things, like you don't necessarily have to build just a register. You can have, like for example, a counter in there. So your program counter works like this. I gave you the code for that in the lecture, but the program counter has the logic for incrementing embedded inside that sequential logic, that always statement. So instead of having an input D that goes to Q, it just counts every cycle, right? Synchronizes the clock. So you can, in this case, this example counts up and counts down or resets. Okay, so use registers. In our case, we're using registers for pipelining, right? And the program counter. So we've got a program counter and we got pipeline registers. The pipeline registers are designed to break the execution of each instruction into 3 stages. So the idea there is that if you executed instructions in one cycle, you would have a very long chain of things that have to happen for each instruction, right? You'd have to fetch, decode the instruction into control signals, and then activate the ALU and write the value back in the register file, all within one cycle. That's a lot of things to do in one clock cycle. So we break it up into 3 cycles and then have 3 instructions being executed in parallel in order to speed up the throughput. And I'll talk more. I have another lecture about timing analysis where I'll talk specifically why having those long paths are bad. Another thing you may want to do with synchronous logic is build a finite state machine. You guys ever heard of that? State machine? Okay, so a state machine is a circuit that introduces sequentiality, where the circuit could, if you have something that requires multiple steps sequentially to perform in hardware, you have to use a state machine. Make sense? You guys say, what do you mean? Like, software is always sequential. Now remember, SystemVerilog is concurrent, has concurrent semantics. So if you write Verilog, everything in the Verilog code is happening at the same time. It's circuits that are concurrent. But what happens if you have some hardware operation that you have to break it into phases? Makes sense? Then you have to use a state machine. A finite state machine is a way to describe that behavior. So it's defined by, it's a sequential logic circuit, so it has inputs and outputs, but it has a set of states which represent the kind of modes of operation it can be in. And so let me give you an example here. So here's a really simple, kind of trivial example that the textbook has in it. I got this from the textbook. So this is a traffic light controller. And the idea is that you have an intersection of 2 roads called Academic Avenue and Bravado Boulevard. And you have a traffic light on Academic and at Bravado, right? And you also have a sensor on both streets that sense when there's cars waiting at the intersection at both streets. So your inputs are TA and TB, which is the traffic detector on Academic and Bravado. And you have the actual light, the traffic light at Academic and Bravado, which is L sub A, L sub B. So TA, TB is the traffic, LA, LB are the lights, right? So you define a state where the light at academic is green and the light at Bravado is red. And we're going to assign that to be our reset state. So when you reset the system, that's how it comes up by default initially. And then you create 3 more states that represent in total the 4 modes of the intersection. So you can have a green light on one road and a red at the other, or vice versa. Or you can have a green yellow on one road and a red on the other. So there's 4 different combinations. And so you represent each one of those states as like a vertex in a graph. And then you have arrows that connect them that define the state transitions. How do you get from one state to the next? So if you have a green light on academic and a red light on Bravado, as long as you have traffic on academic, you want to stay in that state. So you have this loop back transition. Okay, so TA and TB are binary, and the LA and LB are trinary, because you have to have red, yellow, and green. So they're 2 bits. Those light signals are 2 bits, right? And so if you have traffic on, like I said, as long as you continue to have traffic on academic, you're going to keep that green. And in this case, there's no like timer that'll time out. It'll just stay green indefinitely until we have no traffic on academic, in which case it switches to having a yellow on academic and it keeps Bravado blue. It keeps Bravado red, and it'll stay in that state for 1 clock cycle. So in this case, the clock period has to be set up to be the amount of time that you'd be in that yellow light would be on. So this would be like a clock period of, say, I don't know, 5 seconds, 10 seconds, something like that. So it'd be a very slow clock, right? In reality, you'd have some kind of external timer, and that would signal. You'd wait for the timer to reach some point, and that way you could run the clock faster than the time. You could run the clock faster. But in this case, we just adjust the clock to be the yellow light time, and then so then you have this unconditional transition that comes into this state where we've switched now academic to be red and Bravado to be green, and we'll stay in that state for as long as there's traffic on Bravado. And in the instant there's no traffic on Bravado, we'll switch Bravado to yellow, academic to red, and stay in that state for 1 cycle, and then go back to green light on academic. Does that make sense? Okay, so it's it's really simple state machine. And so to build this in hardware, you have to create a state transition table. So this is basically just a truth table that relates the state and the inputs to the next state. So the current state is labeled S, the next state is S prime, and the 4 states are S0 through S3. And the inputs, I mentioned that the traffic sensors are binary. And so if you're in state 0, which is where you have a green light on academic, as long as, as long as we have traffic on academic, we're going to stay in the same state. So this next state will be S0, right? However, if you have no traffic on academic, then your next state will be S1, which is where we have the yellow light on academic, right? So if you're in that yellow light state, then your next state is S2. And we use don't cares here, X's, to denote when we don't care what the value is. And so whenever you have an unconditional transition from, in this case, the yellow light state, we don't care what TA and TB are. We're just going to go to S2 as our next state. So the next time we get a clock tick, clock edge, we're going to go to S2, which is the green light on Bravado. You guys with me? Does that make sense? Okay. Now, notice that when we're in a green light on academic, we don't care what the traffic on Bravado is, right? We only care about the traffic on academic. So you can fill this truth table out where each one of the rows of the truth table corresponds to one of these arrows, right? I think that's right? 1, 2, 3, 4, 5, 6 arrows. So there should be six rows. Yeah, 6 rows, right? 1 row for each arrow. Okay, so then the hardware is going to have an encoding for each one of those states. So we need a binary encoding for state S0 to S3, and there's, you don't, at a minimum you need 2 bits because the log base 2 of 4 is 2. But you can actually use more bits for that encoding if you want. But you just have to assign a unique binary value for each state, and then you would replace the state with the encoding. So S0 is 0, 0, S1 is 0, 1, S2 is 1, 0, and S3 is 1, 1. And so once you do that, you have a fully binary truth table, at which point you can translate this truth table into Boolean algebra, right? Like using the techniques you guys learned in 211. In this case, the next state, so the output of this logic is the next S1. So by the way, once you split these states into binary values, we now have S sub 1 and S sub 0, which are the 2 bits. And so you have to generate a circuit for each one of those bits of the state. So there's a separate circuit for S1 prime and S2 prime as a function of both the inputs and the current state. Right, you guys with me? So there's 2 Boolean algebra expressions for the 2 state bits. Okay, so that just determines the transitions, and then there's a separate table you have to have where you translate the current state value into the outputs. So we have an encoding for the outputs, so the light at academic and the light at bravado is a trinary value, green, yellow, red. So green is 0, 0, yellow is 0, 1, red is 1, 0. It's just the arbitrary mappings that we have there. And then for each state, we have a light setting for the light, the corresponding light, and then that gives you 4 output bits from the output logic table, and you can describe that with 4 Boolean algebra expressions. Make sense? All right. Now, by the way, notice that the outputs are only a function of this current state. You can also have the inputs here as well as input. Like the traffic sensors could be columns on the input side if you want. If you do that, that allows you to basically have the output be its own little truth table relative to the inputs for each state you're in. That's called a Mealy machine if you do it that way. If you do it this way, where the outputs are only a function of the inputs, it's called a Moore machine, right? In a Moore machine like this, the outputs are synchronous. The outputs only update when you change states, whereas in a Mealy machine, the outputs could change within a state if you also manipulate the inputs inside of a state, right? Okay. Okay, so in Verilog then, so that was, I showed you the Boolean algebra implementation. When you do a state machine in Verilog, well, in SystemVerilog, this is actually specific to SystemVerilog. In regular Verilog, you have to actually choose your own state encodings manually. But in SystemVerilog, you can create an enumerated type for the state. So and that's what I did up there. I have type def enum logic 1 down to 0. You still have to give the number of bits for this enumerated type. So I said it's a 2-bit signal, but I gave it actual symbolic values that can go there. And I call it state type. I think I showed you last lecture how to do that in the lab 3 for the instructions. Did I show that? So these enumerated types are kind of cool because if you have a signal in your CPU that output that is of an enumerated type, where the enumerations, the mnemonics for the instructions, then you can have it generate what instruction you're executing, right? You guys with me? Like in English. Like you can have the English mnemonic in Model Sim using this just as a debugging, it's just a debugging tool, right? It's easy to do because otherwise, like he was saying, like it crashes when I get to the subtract instruction, right? How do you know when you're executing the subtract instruction? It's just the machine code, right? But if you have that, if you have a little debugging feature, I mean, you would know if it's the third instruction. I mean, you could see it's the third instruction, must be subtract. But if you have an enumerated type and you have a signal declared with that type, and you can actually have it print subtract at that moment in that clock cycle, right? You guys with me? Okay, anyway. But for the state machine, you can use it to label your state. So I have S0 through 3, which are really horrible state names, by the way. The state names should have been like academic green, academic yellow, bravado green, bravado yellow, right? That would be more informative to use a state. Yeah, it's more typing. The reason these come from the textbook, so I use the textbook names, but I think those are dumb names. Because I don't know what S2, like what is S2? Well, S2 is when bravado is green, right? But you'd have to go back and look. So anyway, so you have so then I declare current state and next state with those types, and then I have this always here that basically just says, whenever you have a pause edge clock or a pause edge reset, if it's a reset, I go into S0, that's my reset state. Otherwise, I'm going to take whatever the next state is and make it my current state. So this is the only sequential logic block you need to have. This is called the clocked logic, right? Guys with me? It just controls the clocking, the synchronization. Then you can have another always block, which is combinational, that implements the next state logic, because the next state logic is combinational logic, right? So this is going to set the current state, I'm sorry, this is going to set the next state, rather, as a function of the current state and the inputs, right? So this says, for example, if current state equals S2 and the traffic sensor at bravado is 0, then I'm going to set my next state to be S3. So I create this combinational logic with an always just to create this behavior, basically, right? Except instead of, I don't have to write it up as Boolean, I can just write it in Verilog, right, with an if then else, and using the names of the states. You guys with me? Okay, and then, right, so basically you write this code, and it will probably generate this logic or something similar, right? Something equivalent to this logic, this Boolean logic. And then it should generate a schematic that looks like this, right? So you can see that the output here is S. So the next state is S sub 1 prime, S sub 2 prime, right? That's the next state, the next state of the two state bits. And those are the inputs to the flip-flop or the register. And then the output of that register is the current state, right? So this thing is the clocked logic, and then these gates here are the next state logic. You guys with me? Obviously, you don't have to build, you're just writing this, and then you're hoping that it's going to synthesize into the corresponding hardware. And then the output logic is similar. You can have another always block, another always statement, and you can assign the output as a function of the current state using just an if then else, right? And so that should, again, generate this behavior with something that looks like that logic. In this case, the output logic is just these three gates. Make sense? Okay. All right, so then you end up with a timing diagram. When you simulate this thing, you're going to want to put you want to plot next state, current state, light on academic, light on bravado, and you run your clock, you reset it. When you reset, that's going to reset your current state to 0. Okay, and then every time you have a rising edge of the clock, whatever's in the next state is going to transition to the current state. So, for example, we have a few cycles. Cycle 2 and cycle 3 is where we just have a green on academic, so it's just staying in state S0. At some point, the traffic sensor on academic drops, which will correspondingly drop or set the next state to the yellow light on academic, right? But that won't take effect until the next rising edge of the clock, at which point it'll become the current state, right? So there's a lag between the next state. So in other words, the next state is going to update right after the traffic sensor goes to 0, but there's going to be a delay because that won't go into the current state until the next rising edge of the clock, right? And then remember that S1 is the yellow light on academic, so you'll stay in that state for a fixed amount of time, 1 cycle, because you're going to go to S2 on the following rising edge, right? And then once you're in S2, you're going to stay in there until the bravado traffic is 0. So there's the bravado traffic going from 1 to 0 there, which is going to cause the next state to go to S3, but that's not going to do anything until the next clock edge, at which point the current state will become S3, right? And then S3, of course, is a yellow light state, so we're there for 1 cycle and we automatically go to S0. Make sense? So when you plot these in ModelSim, it'll actually show you the names of the states if you use an enumerated type. Okay, I mentioned that the encoding for those states can be binary, or you can use one-hot encoding, where, you know, if you have 4 states, you use 4 bits, and one of those bits is 1, depending on what state you're in. You don't have to decide that, though. If you use that enumerated state in SystemVerilog, it'll decide that. Although, even when you use an enumerated state, you have to tell it how many bits it's allowed to use, right? So we told it it's only allowed to use 2 bits there. So the synthesizer will choose the encoding, how to map each one of those states to a binary code, okay? Okay, so here's an example question. I had this on an exam back in fall 2018. You're designing a controller for an elevator in a 2-story building. The controller has the following inputs provided by the buttons outside the elevator. The inputs assert when a user these inputs assert when a user presses the button and deassert automatically when the elevator is on idle on the corresponding floor. So we have an input called first floor request up, second floor request down. Controller has the following inputs connected to the buttons inside the elevator, which assert when a user presses a button and deasserts when the elevator reaches the corresponding floor, meaning that, you know, that's just defining the transitions, floor 1 and floor 2. And then the controller has outputs, meaning go up, go down, basically. So there's 4 inputs. There's a two inputs corresponding to the buttons outside the elevator, 2 inputs corresponding to the buttons inside the elevator, and then there's a signal that tells it to go up or go down, right? So you have to keep track of essentially where the elevator is and what it's going to do next. So the solution here was just to create 4 states. There's a state for first floor idle, second floor idle, state for first floor going up, and a state for second floor going down. And basically, if you're on the first floor idle, you'll transition to first floor going up when, you know, you get a request, you know, to go up either from the inside buttons or the outside buttons. Make sense? All right, so it's pretty simple. It's kind of like the traffic light controller. You have these loopback transitions that'll tell it to stay put if it's basically idle and there's no requests. Does that make sense? Okay. Okay, so here's another example. This one is a divide by 3 counter. So this one counts from 0, 1, and goes 0, 1, 2, and back to 0. So you can see that we have, in this case, 3 states. All the transitions are unconditional. We have the next state logic that, you know, that's pretty boilerplate. You know, basically, if you have a reset signal, you set the state to the reset state. Otherwise, you set the state to be whatever the next state is. And then the next state logic is also very simple because all the transitions are unconditional. So we don't look at the inputs. In fact, there are no inputs here. And then the output logic is basically just saying assign Q equals state equals 0. So Q is only, oh yeah, Q is just basically a 1-bit output that just is asserted in the S0. So it's basically 1, 0, 0, 1, 0, 0, 1, 0, 0 as it flips through. Okay. All right, so let's take a look at a more realistic example then. So controllers are, so by the way, just to be clear, if you have an elevator controller or a traffic light controller, it's probably going to be controlled by software because it's easier to write software than a state machine, right? You just write software on a microcontroller And that's because the traffic light and the elevator are not operating, they're operating at a very long time scales, right? So you can afford to just write software, right? But what about an example where you actually have to design a state machine controller? When would you have to do that? Well, that's whenever you have things going on at the time scales of the clock, right? Like single clock cycles, right? That's when the dynamics are too fast to use software, where you have to use a hardware controller, right? And I think one of the most common examples are bus protocols. So the most common one is AXI, which stands for, it's the one that's in everyone's phones, basically. It controls basically all the consumer embedded systems. All the ARM processor-based systems. So it stands for ARM Advanced Extensible Interface, and it's a master-slave interface, and it's used for programmed I/O transactions, meaning that it's when you've got the CPU can issue read or write requests out to peripherals. You guys with me? And the peripherals that are targeted according to their address. So each peripheral has an address range, and if you read or write to the address range corresponding to a peripheral, it goes out on the bus, and then there's auxiliary logic that routes that request to the peripheral. You guys with me? So if you design a peripheral, you have to put these AXI interface on it, right? You have to be able to talk. That's the language, basically. That's the language that all these modules speak inside a system on chip. Yes?
It's kind of like the protocols where it sends the same thing to every device, but only certain ones are like, they're looking for a certain system that know that they're supposed to act on that information.
Yeah, that would be like a bus type architecture where they all are hooked into one bus, but modern chips use a switch. There's a switch interconnect. So instead of a shared bus, there's these arbiters, there's these switches, well, they're switches actually, they're crossbar switches, where the master has a port on that switch, and the switch is aware of what the address ranges are, what the I/O ranges are, and based on that address, it'll route the request to the appropriate output of the switch, and it just goes to the one peripheral.
Okay.
That way you can have multiple things going on at one time.
Yeah,
right? And all the connections are point to point. So everyone connects to a switch. So everyone that wants to communicate on AXI will just basically have one connection to the switch, and then everyone that wants to receive a request from AXI is a one connection from the other side of the switch,
okay.
right?
Thank you.
Okay, so AXI is so the idea behind AXI is that it's a high performance protocol. They want to be able to support multiple outstanding requests at one time, and they want it to be full duplex. So you should be able to read and write at the same time, and you should be able to have, you should be able to issue 10 read requests before, the first one responds, right? In other words, they want to support multiple outstanding requests in flight. Does that make sense? Right? So it's not a simple thing where you just put in you send an address out and read, and then you wait for the response to come back. You don't want to have to wait for the response to come back because that's going to lower your utilization, right? You want to be able to have, you want it to be more flexible. So the way they solve this is the bus has actually 5 different channels in it. There is a read address channel, a write address channel, read data channel, write data channel, and a response channel. So if I want to write to the bus, I want to send something to a peripheral, then I would send, instead of saying I want to write, you just put the address that you want to write to out on the write address channel, right? And because you've chosen that channel to put the address on, it's implied that you want to write, right? Okay? Likewise, the read address, if I put an address out on read address, it's implied I want to read. And then the data is then sent on the corresponding channel. So there's a read data channel, a write data channel. Does that make sense? So I can read and write at the same time, basically, right? And then there's a response channel that allows for an acknowledgement mechanism. It allows me to know that my request worked, right? And that's a separate channel. That makes sense? So the channels are labeled the AR channel, AW channel, R channel, W channel, and B channel. And this is, by the way, just to emphasize, this is the state-of-the-art bus protocol. This is what is currently used to connect everything inside an iPhone processor, even to this day. Now there's some other features, by the way. There's burst modes where you can do a read, and you can send one address and tell it that you want to do 16 reads from that address, and so it'll burst 16 values back on the read data channel. So it has some, and also has security features where you can have levels of protection. There's a lot of stuff going on, but this is just the basic concept of how you do single transactions. Okay, so basically, whenever I do, this is an example for a write. So there's also this handshaking protocol that has to happen, where if I want to put an address out on, say, the AW channel, the AW address, meaning I want to do a write. I want to write to an address. So the master will say, you put the address out and you put the valid. You say, I've got an address and it's valid. And I have to hold it there until the other side of the connection, whoever that address is referring to, has to come back with a ready. Right? So that's the way that it's like a handshake. I say, I have an address, it's valid, and I got to sit there and chill until the other side comes back and says, okay, I'm ready. Right? At which point I can assume that I've now registered my request for the read, and I can deassert the address and I can drop valid. Does that make sense? Okay. Then, once that happens, in this case, I'm doing a write. So because that was on the write address channel, then I got to send the data I want to write to the other side. That happens in a different phase. So now I've got the address out there. I got to send the data I want to write. So the same thing happens. I put the data out on the write data channel, and I assert the, oh, sorry, I got it wrong. I wait until the write ready signal comes up from the other side. So I have to wait for the target to tell me he's ready for the data. You guys with me? So it's almost like the opposite. I got to wait for him to be ready, at which point, once that ready goes up, then I can wait for several cycles optionally if I want to. But when I'm ready to send the data, I send the data on there and I say the data is valid. Make sense? And then I do that for one cycle per word. And when I'm done, you assert the W last. That's the last word. In this case, I only had one word, so the first word was the last word. Make sense? Okay? Then I have to wait to see if that write worked. I have to wait for the other side of the channel to report back that everything's okay. So that comes back on the B response. So for that, I have to assert be ready, signaling that I'm ready for a response. And then eventually I'll get a response code and a valid for the response. And there's different response codes. One of them is okay. It means everything went fine. Another one says, something went wrong. There was an error. Make sense? It's kind of confusing, but that's the way that's the way that AXI works, at least for a write. Okay, so let's say now I want to create an interface for this, which is something that if any of you become hardware designers, you're probably going to have to do this, because by creating a AXI interface for your hardware design, it means that you can drop your design into any system on chip that has an AXI bus, which is basically all of embedded systems use AXI. Make sense? So you can design something like, say you design a neural network accelerator, right, of some kind, or like Apple has the neural processor unit, the NPU, right? That NPU is a slave peripheral that just gets dropped into the SoC, and it speaks AXI, which allows the ARM processor on there to send it work to do, right? Or the image processor or the GPU. All of those things are peripherals that go in there, and they can communicate with the rest of the system through this AXI language. So you might have this product interface design that allows your application logic to talk in a very simplified way, where you can just say, I just want to write, you give it a write address and write data. And then you allow this block, this module, to translate for you. So it'll take, you know, the application logic just says, here's what I want to write, and here's the address, go take care of it for me. And then this guy will take care of all the handshaking required to move that data through onto the AXI bus. Make sense? So basically the idea is that on the left-hand side, I have a very simplified interface where I've got clock and reset, and then this thing just writes. It doesn't know how to read. So I'm just going to say, this is my write. I want a master interface that can write. And so what I do is if I want to write, I just give it an address and data, and then I just give it a write enable signal, right? And then it'll come back with busy while it's working on sending that write request out, and that way I know when it's done. And if there's an error, it'll send an error flag out. That's real simple, right? However, on the other side, this is the part that's going to connect to the bus infrastructure on the chip. This is the side that's going to have the AXI protocol on it, right? So the question is, how do I design this thing? Well, the problem is that I have to do a design that's sequentialized. It has to go through these phases, the handshake process. It has to go through the address part, the data part, the response part. It has to walk through these steps. And doing that in Verilog, just in pure Verilog, would be difficult because you need a framework for not only synchronizing but going through these steps. So this is typically what you'd use a state machine for. So this is my state machine for this. So I have 1, 2, 3, 4, 5, 6, 7, 8 states. There's an idle state that's also my start state. That's basically whenever nothing's going on. And notice that in idle, I'm assuming that I've got default output. So the busy output and the error output are just 0. And all of the outputs to the bus are set up to be innocuous, basically, where, write valid and be valid and write last are all zeros and AW valid zeros, meaning I'm not engaging the bus. So all the default values are like, don't do anything, right? And then if I get a write enable from the user logic, my application logic, if I get a request for me to go and send a value out on that bus, that will be triggered by the write enable being high. So that'll cause me to go to this request to send address state, which I will basically use to set, first of all, I send busy back to my user to tell him that I'm on it. And then I set the AW valid to be 1, because that's the first step. You have to say valid is 1, right? My address is valid. Now the address output is not shown, but the idea is that the address output is going to be whatever the address input is. So I'm just going to take whatever the address input is here, the right address, and I'm going to just connect this directly to the AW address, right? I don't know why I didn't show that. That should be there. Yeah, that should be there. It should say, sorry, it should say AW ADDR is going to get the right address. Right address, right? Is that what I called it here? Yeah, right address, sorry, yep. Right, so basically I tell the AXI bus, here's your address, and it's valid, and I don't have to tell it I want to write because it knows I want to write because I'm using the address write channel, right? Okay, so you set that up, and then my job is to wait until the ready is 1. That's the value back from the bus. That's going to say, okay, I got it. I got your address. I got your request. At which point I go, oh, actually, I'm sorry. No, I did have, sorry. Got ahead of myself there. Scratch that. The way I have this set up is I send the request first, and then when I get the ready back, then I put the address out on the bus. Sorry. Yeah, so I wait for the request, I wait for the ready to go high. That's how the timing diagram works, right? So I send the valid out, and as soon as the ready comes out, then I put the address. Yeah, so technically, you notice that the address was asserted at the same time as the write valid, but in this case, I'm going to wait to the valid comes high before I put the address out. I don't think that matters. I'd have to I think that should be fine, right? Okay, so the point is that I wait for the bus to be ready. I send the address out. I do that for one cycle. And then I go to the next state, which is where I wait for the data bus to be ready, right? So the next phase of the operation is I have the address registered, and now I have to wait for this guy to come online, this write data ready. Once that comes up, then I can send my data and my valid and my last, right? So I sit waiting for the ready. I'm waiting for write ready, at which point I set up my write data, my write valid, my write last. I'm still setting busy to 1 this whole time, by the way. All these states have busy as 1 except for idle. And then I do that for one cycle because I'm not doing a burst transfer. I'm just saying one word at a time, just writing one word. You can write more than one word if you want, but I'm only doing a single word transaction. So this is an unconditional transition here, at which point I say, okay, I'm ready for the acknowledgement. B ready is 1. I stay there until B valid is 1, in which case I go to the get response, and as long as the B response is okay, then I just go back to idle. Otherwise, I go to that error state and say, I give it an error message, and then I get locked up in there. I get hung. I get trapped in error state. So if there's an error, I just kind of lock up the whole interface in this case. Probably I should have a transition back to idle and just, or have like a clear error input that brings me back to idle, but I didn't put that in. Does it make sense? So what is the point here? The point is that I need at least 8 states in order to do an AXI write. And I can't do this with software. You can't bit bang. Have you ever heard the word bit bang? Bit bang is when you use software to control like a bus like this. Like you want to use software to manipulate the bits to create an interface, to communicate over bits. You can't bit bang because the software wouldn't be fast enough to do this. This is happening at single cycle granularity, at timing, right? So the state machine is there to be able to walk through these states at the cycle by cycle granularity faster than software would be able to respond to these signals. Anyway, that's a more practical example. Okay, so then I put the implementation in here, and basically I split it. Again, I've got the clock logic, or I've got the enumerated types there, the enumerated type for the state. I've got the clock logic here, the next state logic here. The next state logic I use, in this case I use a case statement. You can use a case statement instead of just an if then else. So I have a case for every state. The current state, I check the inputs and generate the next state value. The next state value is just nothing happens to that until I get the next clock edge, at which point it becomes the current state. And then the output logic is, it's using a Moore style machine, I think. Yeah, it's Moore style because all of the if statements in here are only looking at the state, not the inputs, right? So basically the outputs are driven as a function just of what state I am. Make sense? And so that's an AXI interface for writing anyway. In reality, it would have to support reads too, so it would be bigger than that. Any questions? Of course, you'd have to design one of these for the other side too. This is for a master port. If you had a slave port, you'd have to have a similar arrangement where you have a state machine that interprets things from the bus and then puts the values out to the user logic. Okay, all right, great. Any questions about that? Okay, so I have a few minutes left. I'm going to just introduce the next topic, which is timing analysis. Okay, so at the beginning of the semester, we talked about logic circuits. They have inputs, outputs, functional specification, and a timing specification. We didn't talk about the timing specification. So what is that all about? Okay, so when you simulate in Model Sim, you guys haven't had to worry about timing. Delay, I should say. You've had to worry about timing in the sense of clock cycles, right? You have to synchronize things to clock signals. But every time you have logic, the output changes anytime right after the inputs change, right? There's no delay. There's no propagation delay between the inputs and the outputs of the logic circuit, right? And that's because Model sim doesn't know what those delays would be. It's just a functional behavioral simulator. It's simulating the behavior of your Verilog code. It's not aware of the technology and how fast the technology is, how fast the logic circuits are, right? So in Quartus, when you synthesize your design, we gave you the constraint. There's a constraint file, an SDC file. It's part of your project. You might not see it if you use our scripts. By the way, has there been any issues with the scripts? You guys use CSCE 611.sh compile. It compiles it in the program. Okay. Okay, good. So I had one of my past students automated that. So, but what the problem with automating is you're not seeing everything that goes into that project. One of the things in that project is a pin mapping file that maps the names of your top level inputs and outputs to specific pins on the FPGA. The other part is a constraint file that says that you need to synthesize this so it runs at 50 megahertz, because we're assuming a 50 megahertz clock, which means that 50 megahertz is a 20 nanosecond clock period, which means that your worst case logic delay of all the combinational circuits in your all your data paths. The data path is when you have a memory element, a flip-flop output that goes through combinational logic and then goes to the input of another flip-flop, right? That's a data path, right? Your CPU operates in terms of data path operations. The worst case timing, the worst case delay for a data path has to be 20 nanoseconds, right? And so if you try to not pipeline the CPU, you try to make it a single cycle CPU and do everything in one cycle, you'd probably violate that 20 nanoseconds and the compile would fail, but you might not know why or what's going on, right? It would be or it would just take a really long time to synthesize because it would have to struggle to meet that requirement. You guys with me? So the timing specification is where you're saying what the clock speed that you want is, essentially, right? Specifically for combinational logic, the timing spec would be the amount of time it takes to propagate, and that's comprised of propagation and contamination time, and I'll talk about that in a second. For sequential circuits, it's the minimum, the clock period. Minimum clock period. Should be maximum clock period, actually. Maximum clock period, right? That defines the maximum clock period that I'll tolerate, right? Which is the minimum clock frequency that I'll allow. You guys with me? Because period and frequency are inverse, right? Yeah. So sorry, that was a typo. Maximum clock period, the longest clock period you're allowed. Okay, so yeah, I talked about at the beginning of the semester, I think you guys, I'm sure at this point you realize that when you simulate now, you only care about if your circuit works. You don't care about making it faster, making the clock faster. And so you have this, in the simulator, they have this epsilon delay, which means that when you have an input change, the output changes not at the same time, but after a delay, but the delay is infinitely small, right? So, when you guys run in Model Sim, you have to run the simulator, you have to advance the simulator to see changes, but you don't care how much you advance, you don't care what the clock time is in the simulator, right? It doesn't matter. In fact, in your test bench, you could use 1 unit, you could say set the clock high, delay for 1 unit, set it low, delay for 1. It doesn't matter, right? It's irrelevant. You have to have some passage of time, but it doesn't matter how much there is. Okay, but in reality, when you have a logic gate, there is a delay between the input changing and the output changing, the corresponding output changing. There's a delay there. The input changes and then the output changes. So this is a buffer gate. Doesn't do anything. It just passes, but it's a gate, right? Does anyone know why there's a delay there? Do you know what the source of delay is? Anyone think about that? Why is there a delay? Well, there's a delay because this is a RC circuit. This circuit has resistance and capacitance. In fact, digital logic fundamentally uses capacitance to create these logic gates.
Got to fill up the capacitor first.
Right, exactly. Yeah, it takes time to charge and discharge capacitors. And that time is generally just the resistance times the capacitance. Believe it or not. It seems too simple, right? The time in seconds in the units of seconds is the resistance in ohms times the capacitance in farads. It just happens when you multiply those two, you get seconds. Crazy, right? It seems too simple to be true, but that's literally what it is. It's the RC constant. And the capacitance, well, what do you want to do? You want that delay to be minimal, right? So you want low capacitance and you want low resistance, right? The problem is you can never get to zero. Well, you can't get to zero resistance unless you have a superconductor, but you can never get to zero capacitance because the way these gates work is they use a capacitor to turn on and off the transistors. They use charge. They charge the gate of the transistor, which attracts minority charge carriers into the channel of the transistor, which actually makes the transistor conduct from source to drain. So you can never get rid of it. But also wires have capacitance. So when you run a wire, that wire is running over a ground plane, right? So you basically have wire, silicon dioxide, which is a dielectric, and then you have another conductor, semiconductor under it. So every wire is a capacitor, and the longer the wires is, the more capacitance they have. So the longer the wire run, that's what the tools are actually doing, by the way. When you place en route on the FPGA, you're trying to get the wire lengths to be minimal. So you're trying to put all the gates that drive the signal and all the gates that receive the signal, you're trying to get them close, right? Except you have fan outs where you have one output goes to multiple inputs, and you can't get them all near each other because you have limited degrees of freedom on a two-dimensional plane, right? So anyway, that's where the delay comes from. But there's actually two kinds of delays you have to worry about. There's propagation delay, which is the longest amount of time it could take from the time you change the input to a gate to the time the output changes. Make sense? That's the longest delay. But there's also something called the contamination delay, which is the shortest amount of delay that you may see there. So it's a range of values, actually. It's the value can change anytime from the time you change the input plus the contamination delay to the time you change the input plus the propagation delay. That's the range of times that the output is considered unstable, right? It's potentially changing any time during that range of times, right? So now the contamination delay and the propagation delay are different, and there's a different reason why they're different for a single gate versus a multiple gates in a logic circuit. For a single gate, you have gates or multiple transistors, right? And you have, in an ASIC anyway, in an FPGA it's a lot, but you have different lengths of wire inside the gate, right? Also, temperature affects gates. They're slower when they're hot. They're faster when they're cold.
Is that because of throttling?
No, that's a semiconductor property, device property.
It's like the opposite.
For whatever reason, the charge carriers inside the silicon.
Isn't it when a wire gets hotter, the resistance increases?
Well, that's true also. Yeah, that's true too. Yeah, you're right. Yeah, that's for wires. Yeah. So, but anyway, there's differences. Temperature affects it. Also, but with a logic circuit, typically when you talk about a logic circuit, you're talking about multiple gates, right? And there's multiple paths through that logic circuit. So sometimes you might change an input that has a short path, and sometimes you'll change an input that has a longer path, because not all the paths to the circuit are balanced. So that's why those may be different. But I think, am I out of time? 2:55. I've been out of time. Yeah, sorry. I'm running late. Sorry. Okay. Sorry. See you guys on next, see you in lab, and then we'll see you in lecture again on Monday. Have a good fall break. Actually, technically, I think I canceled lab on Wednesday because the Friday one is canceled, so we'll probably won't see you till next lecture.